Last time we started with the multiple degrees of freedom dynamic systems, and we said the MDF, we can consider shear building, we can have framed building or continuous structure, and we started the shear building. And I illustrated to you practical cases where you can be able to identify shear walls in a tall structure. Now we looked at free vibration. Basically, for free vibration, we usually start with that for ease of understanding, because a number of components like damping and externally applied force are eliminated, and it makes it easier for us to be able to analyze our structure. But what you realize is that most of the significant vibration that you are going to encounter in real life cannot be free, or will not be free. They can be, but generally will not be free, because we'll be considering about earthquake, about wind loading, or a lateral force like an impact load. So you see, in most cases there will be some kind of forcing function. So today we look at force, but again first of all we remove damping so that we can be able to simplify our equation and understand the concepts. Then we look at the case when you have forced damped vibration, because again we said for real structure, because of the friction within the joint, or because of the different layers of the materials, the inherent characteristic, damping will always, almost in all cases, be there. When you say undamped, free undamped vibration is kind of an ideal scenario, somewhere like even there is no atmosphere, because there is no even the fluid drag because of the as a result of the airflow or something like that. So we are moving from the simplified ideal case directed or heading towards the more realistic but complex case. And again, I said, you see, we are even considering just 2-story building or 3 stories, because the number of equations that are involved continue increasing as the number of stories or the degrees of freedom increase. But once you understand these concepts, you find that even when you do the analysis using the softwares, you shall be able to understand the report. Once you do analysis, for example, you are using StatPro or Procon, you generate a report. And for example, if your work is to be approved by the necessary authorities like the municipal council or county council, you find that you need to generate that report. Not everything that you get from the design needs to be taken for approval. But for you, once you understand what is happening, like, for example, these people would like to see my loading, what is the resultant moment, and from the moment that I'm using to do my design. So you'll be able to understand the report and to sort out the more important aspect or matter from the inconsequential part. And again, the results that you get, you'll be able to understand what is happening, what kind of equations are being solved, and if there is an error or some ambiguous results, you may be able to question that. So that's why we do this manual and the calculation first. We understand what's happening. Then when we deploy the softwares, we are not just doing it blindly. All right. So force damped vibration. So what we are doing from last week is that now we are adding forcing function, and I have done this deliberate. I have assumed harmonic loading case. Remember, from our single degree of freedom cases that we considered when we could have harmonic or sinusoidal, periodic. Then we considered when is an arbitrary loading. Remember, we talked about the step loading or the ramped loading. But now I want to consider a harmonic loading case, because now this is analytical. It simplifies our work. We do not have to go the numerical or the empirical methods that use, for example, the Duhamel's integral. So I don't want to go that, but that does not mean that it's not to be covered in this class. So in that book that I gave you, the reference number 1, they have started with the general case, and in that case they have been able to do quite a detailed work. But for me, I just want to show you the basic steps, and I've used the simplified case of loading when the loading is harmonic. And then consider just a 2-story building with a lumped mass. We say the mass is concentrated at the floor levels, and the columns, the mass are considered to be negative. Not that they don't have mass, but we assume the mass of the slab and the beam is quite large, so we can ignore compared to that of the column. We can safely ignore. Again, remember, for dynamic loading, we only assuming the deformation occurred due to laterally applied load. So we ignore, even though, look at this, for example, the mass here, we are saying the mass is concentrated at the floor levels. So we expect some effect, for example, because of the axial load, we expect some backwarding of the column. If they are long columns, slender columns, we expect some backwarding. But again, we are ignoring that because we are only concerned about the lateral force. So you can see there are a lot of simplification. Why do we simplify like that? Because when you are doing the real design, you don't just consider this separate. For example, you check a building against, let's say, for example, lateral loads, against earthquake, whether it can sustain. Once that passes, then you go again and do your design, the load combination. We use the load combination. For example, the self-weight, the dead loads, the live loads. So for comprehensive design, we consider all of them. But now for us to understand bit by bit, we are considering only the part that contributes to that kind of the analysis that we want to conduct. In this case, the dynamic dynamic and dynamic analysis brought about by the lateral forces. So now the equation of motion, I hope you remember the equation of motion that we had, the mu, and then we said this is m capital, a matrix, and then we'll have the acceleration as a vector, mu plus c. Last time we did not include c, and even now you're not including c because the damping is not yet the consideration. The square bracket, and then the velocity will be a vector. So this equation is, remember we call it the fundamental equation of motion plus ku. The fundamental equation of whether it's dynamic, whether it's multi-degree of freedom, whether it's a single degree of freedom, we said this is the fundamental equation, and then you'll have this as a vector, force vector of externally applied load. So again, we are not considering damping, so that goes. So you only be considering the component due to inertia, so the one with the acceleration, and due to the stiffness of the structure, so the spring constant K. From the equation of motion that we derived for free vibration, now we are including it's the same. The first one is the same because at the first floor level, there is no externally applied force, so we equate it to 0. The second floor level, the equation at the level 2, or the second degree of freedom, now again, the equation is the same, only that we have the externally applied force. Remember this equation, you don't have to cram them. You actually, if you cram them, you are just tiring your brain. You just need to separate this into free body diagram. Remember the multi-mass spring models that we considered, then you separate as a different free bodies, the first story, second story, then you'll be able to generate this equation. So you use the equation of the dynamic equilibrium, summation of forces about the direction x or u, the horizontal direction should be equals to 0. That's how you are able to come up with this equation. And the solution for the steady state response, remember we considered the steady state, and the other one was transient. The steady state will remain, is the motion that will continue after the free vibration have been done away with or have vanished. If you look at this typical solution, so this is for the first level, first degree of freedom, and this is a solution for the second degree of freedom. This is the same solution. You know, these are second order. The first one, this one is second order homogeneous ODE. So if you look at the typical form and the one you considered for first degree of freedom case, they are the same thing. Okay, so that's why I'll be moving a bit faster because we look at this. So now we have the problem, the equation of motion, equation 94. We have the solution. So what remains here is this coefficient. This is the amplitude. This is the amplitude of our motion for our solution. So it's like you have the displacement at any time, because what we are looking at, remember when you apply this force, we are going to get something. This is on the first mode. I hope now you are conversant with the modes, because in the second mode you have another deformed shape. So what we are talking about is this deformation at the floor level. We look at the deformation at the floor level. This is the U1. Then this is the second displacement, which is brought about by the second degree of freedom, which is U2. So we are saying at any time t, the solution for the displacement of our structure can be given by this harmonic or sinusoidal equation. So you see at time t0, you once you know, of course, without even knowing the U1, because this collapses to 0, the structure is still at rest. So what you need to be found out or to be evaluated is what is the amplitude of our motion or solution, and then we'll be able to calculate. We have an equation that can express what is the displacement at the second floor level at a time t is equals to 5 seconds. So this is the solution, this is the problem. So you can take this is the solution, you substitute back to the problem. To do so, we have the displacement u1, u2, and then you have the acceleration. So you need to substitute this directly, and also you need to get the second derivative. You differentiate twice so that you can be able to get acceleration. So you substitute into the solution into the problem, and you cancel the common factor. Sin omega t will be a common factor. You're going to be left with this kind of equation. And this, of course, you can look at them and see they are algebraic equations, simultaneous equations, which need to be solved for us to be able to get what is the amplitude of our motion, u1 and u2. Now, you see, if we have like 10 stories building, we are going to have about 10 equations and 10 equations of motion. So you see, you have u1 up to u10. The equation becomes quite large. And that's why I was saying, although you can do it manually, now that's when you come to deploying the software. But now you already know what is happening. So you can see it's a very simple thing, very, very simple, how to generate these equations. And now we just need to solve this simultaneous equation for us to get the solution of our motion. Remember when you say what is the response, I said you can give the response in terms of maybe you need to get the time history. This is the time, and then the response you need here, it could be the displacement, for example. You want to know at any story at a certain time what will be the value of displacement, or what is the maximum displacement. So maybe you need to get the time history to be something like that, so that you say this is the maximum displacement, and at this time maybe it was obtained at time t is equals to 4 seconds. So you can be able to see the maximum displacement obtained at this time. Can our structure or the material that you have used, can it sustain that magnitude of deformation? That's all that we are doing. You may want to express the response in terms of velocity or the force. What will be the force, internal force that will be experienced on this member? So it's up to you. But for our case here, we are generally sticking with the displacement of our structure, because our concern will be this motion. What magnitude of displacement? How much is it displaced? And then you can start analyzing using the design code. Is that within the acceptable limit or tolerance? Okay. So let's see with an example, a very basic example. If you look at this example, this is the one that we considered in example 8. Only what you have done is to include an externally applied force at the second floor level. Remember, we can also have externally applied force at the first floor level. In this structural design 3, when you design, you'll be designing with loading structure and earthquake using, for example, cantilever method, for example. So you know the forces will be acting on the whole of this wall. So usually we resolve them, like we take a half of this, from a half to half will act at this floor level. The half, this from this level, the force is acting from this level on this face. Remember, it's acting on a face. Okay, the face that you are not towards the paper. So we resolve. For example, if this was a new DL, we make it a concentrated load at the floor level. But that one you are going to cover in design 3 for those who are going to take that option. No, I think that one is for everyone. All right. So in this case, I'm just taking applied forcing function at the second floor. The first floor, the F is equals to F1, of course, now here, meaning F1 is equals to 0 at this level. So to determine the steady state response of the two-story shear building and an external applied force is applied at second floor. So this is a structure that we considered in example 8. So this part is to calculate the frequency. So this part, I've just brought the answers here. You already have them. So we found that the fundamental frequency was 20.6 trans per second, and the second frequency 50.1. And remember, even the modes, you should be able now to sketch the mode. The first mode, the second mode, up to the third mode. I think for manual calculation, you should be able to handle up to the third mode. You can be able to get a determinant up to for simultaneous equation with 3 unknowns using the reduction method, even up to 4 unknowns, or by matrix method. You can be able to solve comfortably those levels. So you should try, because the example that I gave you, or in that book, you have a case whereby you have a 4-story building. So in that case, you should try to see how will the mode be, because with the sign, for example, if you get it's negative, this side is positive. So the first case, you get all of them are positive, so the deformation of the structure in the both is on the same side. You calculate the second mode, you found that A2 was negative, so we found our structure going like this already. Now U1 was negative, U2 was positive. Then you are going to see how, because this tells you the shape of the structure due to vibration at different stories. So different stories meaning different degrees of freedom, different modes. The first vibration that will occur, maybe all the floors will be displaced on the same side. So the second frequency, due to motion on the second floor level, brings about now a different kind of a shape, maybe something like this. So you need to do practice with the examples that I gave you. Now, these are the natural frequency, and you said the lowest is the fundamental frequency, the other higher harmonic. Then the forcing frequency from this equation, you see, this is the nature of your forcing function. This is the amplitude. F naught is the amplitude of the forcing function, and this is the frequency of the forcing function. So remember, it's like what we are saying is like this motion that is being applied here, it's of this form. It could be in sinusoidal form. And we gave an example of a typical case where you can experience this kind of sinusoidal function. Assume a machine is attached here, or a crane, because you have seen the crane. We are constructing a building. Usually we have tower cranes that might be fixed on our structure as we continue building. Let's say that our building is at second floor level, and then let's ignore about the other construction works or whatever you may be considering. Assuming that after the end we reach at second floor level, and then we leave this tower crane here. Then assume that the tower crane, maybe it have got a machine there which have got some rotation motion, such that this crane is moving constantly, it's vibrating or rotating to and fro. So that's a kind of the motion that will be experienced on this structure. If it's attached on this building here, usually they are anchored on the columns. So you see, it means because of I'm trying to show you a typical scenario where we can have this kind of harmonic loading. So that machine itself producing a rotary motion, if it's out of balance, then there might be a motion in this structure, in this the crane, the tower crane. The tower crane will be able now to transmit the motion that will be experienced here, or the forcing function that will be experienced, because it will be pushing this structure at uniform time, going back, pulling and pushing. So that means we can be able to get a uniform kind of a motion being transferred to this structure. That's just for your understanding, so that you can see where we are coming from. We have found what is the forcing function is 20 rad, because this is F naught. This is our F naught. This part, the amplitude of the forcing function. This is the amplitude, the frequency. I used a capital omega to differentiate from the natural frequency of our structure. The natural omega, this is the structure. The frequency, the capital omega, this is the forcing function frequency, right? So you You see, the forcing frequency is 20 rad per sec. The natural frequency is 20.6, and we have the second one 50.1. So the system is not in resonance. Hence, a steady state response can be obtained by solving equation 95. Yeah, if you solve this equation, you'll be able to get the steady state response. Something to mention is that if the forcing frequency is equals to the natural frequency, one of the natural frequency. If, for example, the forcing frequency omega is equals to the capital omega is equals to the small letter omega 1, or the fundamental frequency, now the determinant of the equation that we are solving, our matrix, will be equal to 0. So in that case, we cannot have a unique solution, because we'll have resonance occurring. And if you remember, when resonance occurs, why we can't have a unique solution? Remember, if you remember the way we talked about dynamic amplification factor. Remember the case when we had the amplitude being infinite, yeah, because of the resonance occurring. That is, the vibration of the forcing function is equals to the frequency of the vibration of the forcing function is equals to the natural frequency of the structure. Very high magnitude of the amplitude is experienced. So in this case, we are saying, you see, whenever you have infinite, it means we cannot be able to get the magnitude. So you can't get a solution. So that's why we are saying, in cases where the forcing function, the frequency of the forcing function is equals to any one, it may be the fundamental, the least frequency, or the frequency at the second, maybe the higher harmonic, the omega 2, the omega 3, like that, if you are talking of three degree of freedom system, that is that 3 stories. So in that case, then that means at one point our structure will have very large amplitude, and of course our structure now is collapsed, through collapse. So what we are saying now is, in other words, unless the structure is forced to vibrate at one of the resonant frequencies, unless our structure is, the forcing function, unless the forcing function forces our structure to vibrate at one of the resonance frequencies, then we will always have a solution for our system of equation. As long as there is no resonance, we'll always be able to get what is U1 and U2. I mean, we'll always be able to get a real solution for this set of equation. Okay, so you find that when you come to analysis and you are using a software, and then you do an analysis, then there is an error comes, then you go to the error page. Let's say I'm considering, for example, if I'm using Abacus, I just go to the error report, the message report, and then I view what the error, why did my analysis stop. Then you might find like it's just tell me resonance occurred, or maybe it use another term, maybe like the eigenfactor, negative eigenfactor, eigenvalues, those kind of stuff. So with the knowledge that I have now, that I know if a resonance occur, our structure have already collapsed, I know what happened. I'll be able to interpret that, because the software will be able to be giving me numbers. It will be giving result in terms of numbers. It's for me to understand and to explain, to elaborate what have happened. Okay, all right. So now what I've just done here is that since now you have confirmed that this resonance will not occur, then what I just need to do is the equation 95. You substitute the values that I'm looking at. You substitute for what is K1 plus K2. So you have to go back to example 8, lesson 6, so that you can see that example 8. Yeah, this is the lesson 6. I hope you can see it, where we started with the multiple degrees of freedom. We looked at what are shared buildings. This is the example 8. This is the example that we are coming from. So I have come back here so that you can be able to look at what are these values of K that you are going to substitute. Remember the K, this a single B, we have to convert it to a single column. So you have to find that we found what is the value of K at the first floor level and K at the second floor level. So these are the K1, K2. So we are combining for the two columns, and then you consider the air density, 12 VI over L cubed. So we found K1, K2 is like that. Okay, so let me go back to my presentation. Now we are here. So you have seen what is K1. So the combination. Remember, this is you can say this K1A, this is K1B. Then you need to combine them. So this is K1. It was 4 times 10 to power 6. So 2 of them comes 8 times 10 to power 6. So K1 plus K2 minus M1 omega. You have M1 is 5 tons, so 5,000 kilonewtons, kilograms. You substitute there. Then you have what is omega. I said I'll be saying ohm, so that you can differentiate from the small letter omega. Ohm squared, which is 20. So you just substitute that. And also for the second equation, so you need to confirm this. You work out this equation. So I wanted to exercise your muscles a little bit, your brain muscle. So you work out this so that you'll be able to get this, just a set of algebraic equations. So you'll be able to get U1 as a certain value in millimeters and U2 as a certain value. And therefore now our solution will be, this is the solution, U1, U2. So you need to substitute what is the amplitude, U1, and the amplitude, U2. So our solution will be U1 is the value you have obtained here, sin omega t, and the value value you have obtained here, same omega. This is very simple. This is the steady state response, right? And with this equation now, you see the solution is given as an equation. So it means you might be told to calculate what is the displacement at this point, or what is the force transmitted at the first flow level at the time t is equals to, let's say, 5 seconds. If you ask force, remember F is equals to K times the delta displacement. Okay, so our structure for dynamic analysis, we are considering the elastic case. Elastic case, Hooke's laws apply. So if you are told what is the force that have been transmitted at the first flow level at this time, you have calculated the displacement, you have the stiffness of your structure, the column, the K1, so you can be able to get what is the force. And from the force, if you ask about what is the stress, the dynamic stress, now from the force, you can be able to get what is the stress if you are given maybe the section properties of a structure, or you can even use the equation of simple bedding. When resonance occurs, does the structure fail? Yes or no? Let's say, for example, this material is so elastic. Is it flexible? Very flexible, such that it can accommodate very large deformation up to infinity, right? So it means our structure maybe will not collapse because the material that we have used can allow large values of deformation. But let's be reasonable here. We are talking of real structure constructed of steel, concrete, timber. Timber maybe is the one that can give us, is it timber or steel? Timber can give maximum, the largest. Of course, it also depends. The stiffness depends not only with the materials, but it also depends with the cross section. The slighter the column, the more the deformation that can be allowed. So for practical materials that we use, when resonance occurs, you may almost be guaranteed that failure will start occurring. If not, for example, then it might be destructive. If not auto collapse, then you might have crack emerge. Okay. So in terms of failure, the structure will fail. The failure of structure can be what you call structural damage or aesthetic. In engineering terms, we talk of ultimate limit state and serviceability limit state. For example, why we check a structure against SLS, we design for SLS serviceability is like you have a building or a roof made of timber joist. You don't want a deflection occurring that is so unsightly or so inconveniencing, such that the deflection that occurs can make your doors and windows not to close. If you have used a beam of the lintel, and that lintel you have just used the timber joist, so you don't want the deflection. Although the structure may not collapse, although that timber member or that steel beam will not collapse, but if it deflects such that it affects the openings and closing of the door, that's serviceability. Or if there are unsightly cracks occurring, then you can say the failure have occurred, not the ultimate failure, but when you do a check against serviceability limit state, it have failed. Okay, so it depends with what kind of design you are talking about when you talk about failure. But let's just take it to your mind that when the resonance occurs, we anticipate a certain kind of damage, because again, the resonance may occur, but the amplitude here is small. So what we are saying is that the deformation that will occur is quite large, but not to the point it can outdo the allowable deformation of the material that you have used. Okay, good. Then quickly we want to look at when we have forced damped vibration. And this one I'm just again going to do it very quickly because we have the equation already, and what we are just introducing the same structure, and then we are just introducing damping coefficient. And we say this damping is almost inevitable because we have joints. The joints, there be the resistance. The structure itself tries to restore its original position. Then we have the multi-degree mass spring model, so that you can be able to get what are the free body diagrams. These free body diagrams help us to generate the equation of motion, because from the free body diagrams, you are going to sum at this first free body, you sum all the forces and equate them to 0. Even this one you can bring on the other side, so that you say summation of all these, the K1, this is due to the stiffness, this due to damping, M due to the mass brings about the inertia, and then we have the externally applied force. And then we have now these are the restoring force, these are the destabilizing forces. Because of there's a motion on the second floor. So you see now there is a force, the stiffness due to the column on the second floor will also act on the first free body diagram. So these internal forces, without drawing the internal forces, you might not be able to see the interaction between the different stories, different floors. Okay. Once you do like that, you are able to sum these forces for one free body diagram. Okay. And using the equation of dynamic equilibrium, of course, the status, the forces structure, summation of forces should be equal to 0. Even when a structure is in motion, if there is no dynamic equilibrium, we'll have what we call rigid body motion. Our structure will float in space. Okay. So remember, even though there is a motion going to and fro, like going through to going fro. If there is no balance, if the resultant forces in the dynamic motion is not equal to 0, then our structure will just fly away or float space. So that's why this equation is applicable here. So the equation of motion. So if you compare with the other equation we had previously, what we are adding is the component of the damping and the velocity. These very careful with this dot, because this represents differentiation. This is the velocity. This is the d over dt. This is the acceleration. So it's d squared u over dt squared. So we have included the damping F1, F2. Now again, we make things a bit more interesting. We assume that these applied forces, they are of this form. They are sinusoidal, and we assume they are superposition of both cosine and sine waves. So this equation, the forcing function, can be expressed in complex form. Remember the Euler's relation? So you can express it using the Euler's relationship in this complex form. So complex form enables us, the Euler's relationship enables us to move or to interchange between the trigonometry expressions and the exponential expression, and we introduce the imaginary number I. Again, remember when we started with damping, and we looked at critically damped, over damped, and then at a damped structure. At a damped structure is when we had, or a damped motion is when we had the vibration. It's when we could say there is a motion that can occur. If the structure is over damped, then it's like immediately the structure is the forcing function is applied, the structure comes to rest. The motion decays exponentially. So there's no motion here to analyze there, because it means our structure was just displaced and then came back to rest. So there's no cause for analysis on this. We are not interested in this kind of motion. Well, it could be necessary so that you can be able to see what is the maximum displacement that was experienced in this structure. But for our analysis, we want to see a repeating motion, reciprocal motion, going to and from. And that's why we only said for reciprocal motion, only the other damped structure are of concern. And we found that in the other damped structure, we have both real and imaginary part. And we said that, real and imaginary part. So in this equation, we have the real and the imaginary part. Only the real part of equation 98 is the applied force. And this one you can prove. Yeah, you can prove this. For you to prove this, I would like you to go to the book that we had. Our first reference book in page number 208. Page number 208. There is about just one equation there showing or proving that only the real part of this equation is the applied force. So now, remember, this is the applied force and can be expressed in this form. And now we assume that the forcing function at these floor levels 1 and 2, they can be expressed in this form. So it means they can also be expressed in this form. And so we can substitute for F1t and F2t, we can substitute for using this equation. So that's why we are saying the same equation that we had, equation 96, we substitute equation 98 into 96. So this part. So and then C, we have for the first floor level, the first degree of freedom, second degree. So don't be so much concerned about this. This is the damping, this is the forcing function, and this is the amplitude, the coefficient before the cosine part, and this is the amplitude before the sine part. So that's why if you look at this, you are seeing F cos F sine, FCFS. These are just to this part is just a coefficient, a constant. So they do not have any implied meaning apart from that they are put before the cos and sine. We can just even say F, but F, maybe this F will be different from this F. Maybe this is 10, this is 5. So you have to we're using a subscript to show the difference. All right, so we have now our equation. The solution of this problem is of this form again. So if you look at this equation and you look at where we started in the single degree of freedom case for the damped vibration at the damped, then the typical solution was on this format. So you see, if we started with the multi-degree of freedom, you might not understand where this came from. But from the single degree of freedom, because we could be able to look at the equation and you see these are maybe non-homogeneous second order differential equation. From our ODE, from our study of ODE, we know what is the form, what is the typical form for a second order homogeneous equation, what is the particular solution. If we just look at a differential equation, then we can be able to characterize or classify that differential equation, and then we can be able to suggest what is, or we already know what is the expected form of the solution. So you may wonder why is the solution like this. So you just go back to those notes that we had at the starting, and also any good book on ODE, you'll be able to refresh, because these notes you already have them. You'll be able to refresh on the solution for ordinary differential equations. So only now that remains, because we have the solution, we have the problem, just substitute 100 into 99, 100 to 99. So you are going to work out this. So solve equation for solution for 101, and remember, we retain only the real part. So anything that will end up with I, we ignore it, because I is the negative square root of -1. So it's an imaginary number. So once you ignore or you eliminate, you solve the equation and eliminate the real part, you should be able, from this equation, you should be able to get this. What is U1 and what is U2? What is the displacement? First floor level, second degree of freedom displacement. And so you see, this is our solution. This is we call it the response. The response is the solution. Let's see an example. So you are to determine the steady state response for this story building. Now, the story building of example 8. So we are solving the problem in example 8, or the problem here. We are solving our structure. Our structure is the same, this, right? But now, because there was no damping, so I have given an illustration. So he said the building is example 8, in which damping is shown alongside. So this structure only shows your damping. So the mass is as given. This was 3 tons. This was 5 tons. The values of K are the same. So we have F1, F2, and then you are to assume how to determine the damping. You are to assume that the damping constant C1 and C2 are proportional to the magnitude of the spring constant. Okay, and the factor of proportionality is 0.01. So you are saying the damping is directly proportional to stiffness. To just explain what the implication or the meaning of this. So this structure, the stiffness of the structure brings about the restoring force. But at the same time, you know, the material characteristic, we say the viscous damping is about as a result of the inherent characteristic of the material that constitutes our structure. So you see, the stiffness, the material will influence, because we said the material and geometry affect the value of K. Remember last semester's discussion? So again, you see the damping, because if the material property, if the material is the structure, let's say the concrete, remember, if it's too stiff, then it means the damping value again will be too stiff. So the damping itself will also be related to the material. If you say the material, let's say modulus to represent a material component. So you are saying C is proportional to Young's modulus. Again, we know, of course, that the stiffness is proportional to Young's modulus, Poisson's ratio, and things like moment of inertia to represent geometry. So you see, both of them related to the material, because this is because of viscous damping. This is because as a result of the stiffness. But the magnitude, of course, will not be the same. So this is maybe 0.01 E. This is maybe 1 or something like that. So we are saying then, by equating this, you know, we can equate, because these are direct related, then it means even this one can be related. C can be related to K. And we are saying C is related to K by 0.01 K. So what we need to calculate is what is C1, what is C2. So C1 is just 0.01 times K1. K1 is the effective or the combined frequency. I mean stiffness for the columns at the first floor level. So you're going to get that. Now you have the C1 and the C2. You go back to equation 101. I did not work out this equation. You really need to sit down and work out this, because you need to substitute the values of K1, K2, M1, omega. C1 you have already obtained is 0.01 K1, like that. So you just substitute this equation and you solve, retain only the real part. You're going to get what is U1 and U. Now that will be the response of the shear building. So this is the solution, but this is just an outline of the solution. This equation in itself, you really need to work. If, for example, you are given this problem all the way starting from example 8. So you see, you need to start working out from example 8. By the time you are finishing up this part, if it's a first vibration, then that will take you quite some time. It's about a 20-mark question, right? And I believe that is enough for today. We have looked at post vibration with and without damping. And again, that one marks the end of our multiple degree of freedom, the part that I want to cover, so that you can be able to move to seismic analysis in next class. This is the 7th class. So now I welcome any question. Just go through example 8.5 that is given in our main reference text. Reference number 1, the book that I have told you about. Just go look at that example 8.5. The example 8.5 is the exact example that we are solving here. Only that, of course, the values is this example. So you follow it up. Only that, of course, the value of M, masses are different, the stiffnesses are different, but the structure is the same and the approach is the same. All right. The floor is now open to questions. I think I'll stop the recording.